Hi, my name is Emiliano Ruiz, and I am a student at the University of West El Paso. I'll be presenting the development of a Synchro model for the intersection of Sunland Park Drive and Doniphan Drive in West El Paso. It is noted that this video is created and submitted to fulfill the requirements of CE5361, traffic flow and simulation modeling imparted in spring 2020. Before continuing, I would like to introduce an outline of the presentation. I'll begin with the objective and continue with the site and data information, software familiarization, and the coding of the intersection to include geometry, volume, and timing settings. Then, I'll proceed with the results of the level service analysis and will finalize with the concluding remarks. The objective of this simulation, per the project's instructions, is to code a synchro model of an isolated and signalized intersection and use the model to perform a level service analysis. The chosen software is Synchro Studio 10, which is a traffic signal optimization simulation modeling software. To provide a perspective, the intersection is located approximately 5.4 miles north of UTEP. As previously mentioned, the site involves the intersection of Sunland Park Drive and Doniphan Drive. Based on visual inspection, the site conditions include the presence of commercial driveways, a railroad crossing running in the north and south direction, and a right turn eastbound channelized lane. The data provided include an aerial photography and the traffic count and signal timing information disclosed by the City of El Paso's Street and Maintenance Department. This project was the first time I was introduced to Synchro and therefore had zero background knowledge of the software. However, I became familiarized with its capabilities through a combination of YouTube video tutorials, the user guide provided by Synchro directly, class and student discussions, and the project instructions. Particularly, as with any other software, there are plenty of video tutorials available on the web. I found this resource to be the most useful. Now, we continue with the coding of the intersection in regards to the geometry. The network geometry is controlled in the lane settings menu pictured above. The bottom network provides a summary of the movements from all of the approaches. In the menu, the important parameters to consider are lanes and sharing, street name, and link speed. Let's take the westbound lane settings as an example. The lanes and sharing information is updated to include exclusive left and right turn lanes in addition to 2 through lanes. The street name in the westbound direction is named Sunland Park Drive, and its corresponding speed is set at 40 miles per hour. A similar approach is taken for all the directions. Now, I'll focus on the coding of the intersection in regards to volume. The traffic count data provided by the City of El Paso is firstly analyzed based on 15-minute data counts to obtain the highest volume served in 1 hour. The peak volume was found to be between 5 and 6 p.m. Once this is identified, the individual volumes per movement is input in the same lane settings menu under traffic volume. Taking the same westbound example, in this direction, 113 vehicles were observed to make a left turn movement, 670 through, and 525 a right turn maneuver. The bottom network is updated to display the observed volumes for all of the approaches. Lastly, on the coding of the intersection is the signal timing information. These capabilities accessed in the phase settings. Once the phases are categorized and inputted correctly in the ring conveyor settings, the timing data provided by the city is imported. The important parameters to consider are minimum initial, yellow time, maximum split, and all red time. Pedestrian phase is ignored in this simulation. For all of the left turn movements, I've coded the model to represent protected permissive movements. In the westbound example, the left turn is given phase 3 and the through is given phase 8. However, the left turn maneuver may also happen in phase 8 because the lane is also permissive. The timing information and phase summary are displayed in the top left and right images respectively. The level of service analysis is accessed in the node settings and timing settings once the geometry, volume, and signal settings are updated in Synchro. The node settings provide the overall level of service based on the average intersection delay. The timing settings menu provides the same information, however it is displayed for each movement approach. The bottom network is updated to display the level of service for all of the approaches. It is noted that these results are given for the unoptimized simulation. Synchro provides the option to optimize the cycle length and split to reduce the delay at the intersection. After applying this capability, the results are accessed in the same manner mentioned in the previous slide. This tool allows to reduce the overall level of service from F to D, or intersection delay from 102.4 to 50.7 seconds respectively. After the optimization, all southbound movements and westbound through have a level of service D, and eastbound through and northbound through a level of service E. I'll finalize with the concluding remarks. In summary, I've coded a simulation model of a signalized intersection in Synchro 10, performed a level of service analysis, and have interpreted the results. What I specifically gathered from this project is the fact that the software is simple to understand, operate, and to draw adequate conclusions.